In previous videos, we have mentioned that MOSFETs are highly efficient transistors in terms of power dissipation. For this reason, they are a primary choice in power applications, especially in switching scenarios. But how do we determine the efficiency of a MOSFET? By using the parameter of operational internal resistance. The value of operational resistance directly depends on the gate voltage. For example, for the IRF 540 model, we have a maximum gate voltage of 20 volts, but the drain to source resistance is specified at 10 volts, with a value of 0.077 ohms. The dissipation formula is current squared times resistance. For this case, we will use a load of approximately 2 amps. So with a gate voltage of 10 volts and the established load, we will have a power dissipation of 0.308 watts. Since we're using a 20220 package, the internal resistance is 62 degrees Celsius per watt. Multiplying by the power dissipation, we get a temperature increase of approximately 19 degrees Celsius. Now it's time to verify the value in the laboratory. So here we have the transistor to test. We have a 2.1 amp load. We have the room temperature of 21 degrees Celsius, and we are going to measure how much the temperature rises in the transistor. We don't have a heatsink, so the temperature will rise a little above what we calculated along with other variations of the internal resistance. It is not going to be exactly what we see in the datasheet. There's going to be obviously some variations, sometimes higher, sometimes a little bit lower, but it should be within a range. So we calculated 19 degrees of temperature rise. We should be expecting something around 26 degrees. Let's see how far off we get. We are in the mid-40s. I'm expecting it to rise to 51, 52 degrees tops. And we're doing the measurement in the epoxy body and not in the metal plate. So it is going to be kind of stable between upper 40s, early 50s, as we can see. Do you have a project that needs to be finished? Do you have an idea for a product and you want to take it to the next level? We are your best choice. In PrismaSem Network, we have the best team to do so. We offer services on hardware design and software design. From PCB development, firmware development, app development, and desktop development. We offer competitive prices and an excellent service. Contact us to get a quote. All of the info available at the video description. Now that we have verified the value of the transistor, it is time to look at the MOSFET with superior capabilities, the IXF H48N60X3. This is a transistor with greater power capacity compared to the previous model. For this case, a value of 65 milliohms is specified at a gate voltage of 10 volts. Hence, apart from having a slightly lower internal resistance than the previous model, we also have a larger package and, therefore, greater power dissipation capacity. For this transistor, we will conduct the test with a current of 6 amps. According to the calculations, the power dissipation will be 2.34 watts. Let's then observe the temperature increase in the lab. So now we have this transistor with a load of 4.5 amps. And we have the room temperature. Let's see how much it rises. We can see we're rising above 38 degrees. It should be getting to around 50 degrees tops with this load and the internal resistance we have. So we are barely getting to 40 degrees at this moment. It is going to set stable at 40 degrees for this case, so we can see how efficient it is. Now we have seen how efficient the MOSFETs we've used in the test are, but nothing is really understandable without a reference. So let's conduct one last test with a bipolar transistor to really visualize how efficient MOSFETs are. In bipolar transistors, efficiency is measured by multiplying the current by the saturation voltage. For the tip 31C, it is approximately 1.2 volts. With the same 2 amp load, we will have a power dissipation of 2.4 watts, while with the RF540 MOSFET with the same load, we will have a power dissipation of 0.308 watts. Here we can see the considerable difference. Now let's see the difference in the lab. So here we have the tip 31C NPN transistor, and we have the 2 amp load. We are going to see how the temperature rises. 20 degrees of ambient temperature, let's see how it goes. And it is quickly rising to the 60s. '70s. Remember, we are handling the same load as the first transistor, as the first MOSFET we tested. 80 degrees, 90 degrees, 100 degrees. It is already reaching the unsafe area of operation. So we can see how we have a massive difference of how the temperature rises between the MOSFET and the NPN transistor. With this reference, using a bipolar transistor, we can verify the superior efficiency of MOSFETs. It should also be noted that the MOSFETs used in the test in this video are relatively old, so they do not represent the best technology available, as we can find newer models with internal resistances lower than 30 milliohms, but at a higher price, of course. We can see that solely in terms of load control, MOSFETs are the superior choice. When are MOSFETs a worse choice than a bipolar transistor? That will be discussed in a dedicated video.